Yeah, okay, so welcome back everyone. So today is our pleasure to have Yasamin Jalalian, who will be giving a two-part talk. Today's talk will be about data efficient kernel methods for learning equations and with application to learning differential equations. Yeah, thank you, Yasamin.
Hello, everyone. Thanks, Boumediene, for the introduction. As Boumediene said, today I'm going to talk about a work that we recently put on archive on data-efficient kernel methods for learning equations. And this part is going to focus on mainly this recent paper on learning differential equations. So I'm going to start by motivating a little bit what we focused on. So as you definitely know, PDEs are everywhere, and they're very important to study in different fields of science and engineering. In particular, solving and learning PDEs have been very important problems for many years. And so there has been a whole process of going from analytically solving PDEs to finding numerical methods. And in the recent years, data-driven methods have become very popular for both solving and learning PDEs. And in particular, what I'm going to focus today on is going to be the cases where the physics of the system is unknown or partially unknown, for which data-driven methods are used to approximate solutions in the model itself. And that's going to be the main focus of my talk. So I'm going to start by giving you an idea of what the problem looks like that we're trying to solve in this work. So essentially, all of our methodology and the error analysis that we had in the work applied to a general PDE. But I'm going to focus on a second order PDE for the sake of this talk. So consider having the following equation. As you can see, so this is a second order PDE here. This P here represents an unknown, possibly nonlinear function that actually represents the algebraic form of the equation of the PDE. This F here is a partially observed source term, and the U is a partially observed solution. So we're assuming that the PDE that we have is well posed. We're assuming that we have an idea of the order of the PDE, but we have no idea how the equation is. So we have no idea about the algebraic form of the equation. We have no idea which one of these derivative terms exactly appears in it. All that we know is data only on U and not on the derivatives, and its corresponding data on F. So a little bit more particularly to make sense of what I'm describing here. Imagine having these grids. So we have a set of data points X, and what I'm showing you here is the evaluation, and we have m pairs of functions UM and FM. And so what I'm showing you here is that's the evaluation of these functions at these points X. So the data points X here are the evaluation of these functions on them are the black points on the grid. And then we also have n observation points. So essentially randomly, we take a subset of these data points, and those are going to be the observation points that we have for whatever we're going to do in the future. So here in particular, in this example that I'm showing you, we're assuming that all of the boundary is observed, but that wasn't the case for all of the examples that we had. And so, for example, here, these 2 points have been taken randomly to be a part of the observation set. Some remarks here are that the data points essentially don't really have to be in the form of points. You can have like you can observe a line in the domain. It could have any form. And also, the observation points don't need to be the same between different pairs of functions. In principle, the number of observation points for each of these pairs also doesn't need to be a fixed n, but for sake of notation, we just decided to take a fixed number of observation points per pair to just ease the notation. So now, given this setting, so we have this this unknown form of equation. We have partially observed solution terms and partially observed source terms. what we aim to do here is that we want to learn the function p, and we also want to learn the solution on the continuum. So essentially learning this function p is learning the PDE, and then the functions well, assuming that the PD that we're learning is actually well posed, then this would be akin to learning the solution of the PD. So I'm going to make things a little bit more concrete by just showing you a little example here. Consider the equation of Darcy flow. So if I want to give an idea of how we could approach this, we can take three pairs of different functions, um and fm. So essentially this is u1, u2, u3, f1, f2, f3. And then again, in this example, what I'm showing you, so the boundaries are observed. And then you can see that, so for u1, for example, there's these 2 points. And then for f1, we have observations on those 2 points as well. But then when we move across the pairs, the red points here change. Again, so they don't have to be the same points for the data. And so essentially it could be pretty flexible. And so yeah, so this is essentially the kind of data that we worked for all of our examples. And again, so the goal, just to emphasize, is that we want to essentially learn. So in principle, for the purpose of data generation, you would have an idea of like this equation, you generate your data, then you pretend that you have no idea that this is your equation. You just know that it's a second order equation. And then you try to have an approximation for this that actually represents the P, and then also learn your U everywhere else. So solving and learning PDs with data-driven methods is not new. It's been something that people have been focusing on for the past few years, and mainly the main approaches for learning and solving PDs fall into either one of these two categories of using neural network-based methods or kernel-based methods. In particular, two methods that have been very popular, and we have also benchmarked against these methods in our work, are SINDI and PDFind and PNSR, which I'm going to explain a little bit more in details what they exactly do. So SINDI stands for sparse identification of nonlinear dynamics. And so what they do is that they gather time series data from a dynamical system, then they have a library of good candidates for the terms that might appear in the equation, and they use sparse regression techniques to just select the best candidate terms that would appear in the equation. And it's useful because it gives you interpretable results, and it also works quite well with moderate amount of clean data. The other method is PNSR. So that stands for PINs, physics-informed neural networks, plots against sparse regression. So the way that this works is that, again, given the data and some physics of the system, what they do is that they train a neural network to predict the system's behavior. And then also on top of that, they also use sparse regression to extract the explicit equations from that trained neural network. And so this combines data-driven learning with physical insights, and in general, it handles noisy or incomplete data better than just purely symbolic methods. Now, why we chose kernel-based methods. So there's some advantages to doing that, but in particular, it's interpretable and amenable to numerical analysis, and that's something that we worked on in this paper. It's also, usually the number of kernel parameters to learn is smaller. Then it handles sparse data, and it also comes with a priori error estimate. So some notes on this is that in, for example, this work by Dalong and Bandat Hosseini and other collaborators, and they have already shown that in general, they have already shown some kernel methods that work quite well with sparsity. And also in this work by Badia and Chen and Humano Hadi and other collaborators, they have shown that they have a priori error estimates for solving PDEs. And so on top of these things, what we did in this work was that we proposed a kernel-based method that outperforms not only classical kernel-based methods, but also the state-of-the-art methods when in particular given sparse data. We also compare, and numerically we compared our results to these methods. And also we proved a priori error estimates not only for the solution of the PD, but also for the recovery of our equation function P. So I'm going to very briefly just show you this because this is the classical kernel interpolation / regression result that I'm going to use over and over to simplify the methodology and the optimal recovery problems there. So just a quick reminder that the solution of a problem of the following form is actually a closed form solution of the following form, and it has the following RKHS norm. And I'm going to over and over use these norms to simplify my optimization problems. Okay, so what we did was that we proposed two methods to solve our problem of approximating this P and these UMs in the continuum. So the first approach, which is the more naive approach, is what we call the two-step learning. And in that, what we do is that we first approximate the solutions UM, and then using the approximant of the first step, we learn P. So we first learn the U, then learn the P. And then the second approach that we call one-step learning is an approach that tries to do these things, learning the U and P at once. A little bit more into the details of it. So for the two-step learning, what we do is that we do just a classic kernel interpolation to recover the UMs independently from what the P is. And then we move to the second step. Then, as I mentioned before, so we only had data for these UMs and not for the derivative terms. So then in the second step, we explicitly compute derivatives, and then we can form a similar minimization problem like the one of the first step. And then this again has a closed form solution and then essentially so we can get approximants for both the UM functions and the P function. Some remarks on this this way of approaching things. So in the first step that we're only recovering the UMs, one thing to notice is that first of all, half of the data here is discarded. So we do not keep in any way into account the data that we have on the functions fm. And another remark is that we're not taking into account in any way that these UMs are actually solutions to the PDE. And then on top of that, what happens is that, again, as I said, like we were mainly interested to see like what happens when we have sparse or poor data. So given what we do in this first step, when we move to the second step, what we have to do, because we don't have data on the derivatives, we have to actually explicitly compute the derivative terms of these of the approximants. And for the derivative of the approximant, to give a good approximation of the derivative of the truth, we like sparsity would essentially go against this. Just intuitively, you can imagine that when you have sparse data, then the derivative of your approximant would not really give you a good approximation of the derivative of the truth. And so because of all these issues, just a naive way of thinking about using kernel interpolation would not be a good idea. Again, especially given sparse data. If you have more data, it will probably work well. And I can show this in the numerical examples afterwards. But because of that, so this motivated essentially thinking about this problem and solving it in a one-step approach. And so what we did here was that we essentially formed a one-shot minimization problem. So here we have the first constraint in this optimal recovery problem is the constraint of the solutions, and then the second one is the PD constraint. Now, something that I would note here is that for this problem to have a closed form solutions, you essentially would need to have data points in the arguments of the VM and the Q here, which are the approximants, Again, to note here is that in this particular case, because we're not doing a two-step approach, so we don't have any values for the derivatives. And so because of that, we had to go around this issue by introducing latent variables. And we had to then rewrite this optimal recovery problem in terms of those variables and the optimization slack variables that came here. And now in terms of that, those variables, we could rewrite the problem and essentially reduce it to the following thing. So this is where I was saying that I'm going to be replacing these RKHS norms with these forms. And now essentially here we're ready to numerically solve this minimization problem. When we got to this step, we first started with like working with standard gradient descent methods and Newton algorithms. But we realized that because of the nonlinear coupling of these terms here, they actually resulted in a stiff optimization problem, and that's why it was very expensive to just use gradient descent algorithms, or it was highly unstable to use just quasi-Newton algorithms, and that's why we used a Lovenberg-Marquardt type algorithm, which iterates between these two. And this gave us a much better stability and accuracy. Now, in terms of the algorithm and the methodology itself, this is essentially what we had, and then what we compared for the numerics against other state-of-the-art methods. I'm going to briefly a little bit show you the convergence guarantees and the type of error estimates that we proved for this. So for convergence guarantees for both the solution functions and the PDE function, we essentially needed two types of assumptions to assume, which are pretty realistic assumptions. So the first one is regularity assumptions. So essentially the RKHS of these kernels that we're using has to be embedded in some Sobolev spaces, which is, again, realistic because, for example, for Matern kernels, this is the case. And then another assumption that we had to assume was that as we take the number of points, both in the domain of the solution functions and in the domain of the PD function, as we take the number of points to infinity, we essentially have to ensure that we're filling up the space with these points. There shouldn't be really gaps in these spaces. So ensuring, again, the regularity and the fact that there's essentially no gaps in the domains, we could get convergence results for both the approximants of the solution functions and the PD function pointwise and in Sobolev spaces within the indexes related to these indices of the embedding of the RKHS spaces. Just a minor note was that it was essentially important to have this specific order of these limits tending to infinity for the result for the equations. And then we also got some a priori error estimates, again, very similar types of regularity assumptions had to hold for these results to be true. And so we used an underlying classical thing, which is called, so we used, for all of these, we use Sobolev embedding, but also there's some Sobolev sampling inequalities that are pretty classical when using GPA regression and kernel methods for getting error estimates. But essentially, in principle, doing something like this for the equation function was something that, at least to the best of our knowledge, hadn't been done before. Now I'm gonna get to the numerical experiments here. The first slide that I'm going to show you is the numerical experiments that we had on Darcy flow. So essentially we took different numbers of, this n was different numbers of pairs of functions UM and FM. And then we also took different number of data points and observation points. And we compared our methods against, what I'm going to show you here is that is the comparison of our methods against each other in particular. So let me get to the error plots to give you a good idea of what's happening here. So these are the error plots for the solution functions. And we had two different error measures for the PDE. This is the forward error measure, and this is the operator learning one. First, getting to the solutions here. One thing I want to point out first is that even in the case of taking the maximum number of pairs of functions here and the maximum number of observation points, this is really still in a sparse data regime. Because usually for these sort of problems, you have at least like thousands of points that you take into account, a lot more in this. But so here in particular, I'm showing you the plots that are comparing the one-step and the two-step method that we had that I presented earlier. So in the one-step method, when we're recovering the functions u, as you can see, essentially with the two-step, you can't really see a good decay of the error anywhere, which kind of makes sense because where we're using the two-step, essentially the information between the different pairs of functions doesn't interact with each other. So it really affects when we're discarding the rest of the data and the fact that they come from PD, it really affects very much how well we can recover these things. Whereas with the one step, you can see that it decays. Pretty similarly, you can also see that for both of the error measures that we have here, the one step is over time performing much better than the two step. Now for burgers, I'm going to show you the plots of the comparisons against the other methods. Here, what we did was a bit different. So we only took one pair of function, the example that I'm going to show you. We only took one pair of function, but we took more data points and more observation points. And so something, before I show you the results, something that now that I explained our two-step and our one-step method, it's worth saying that the Cindy is actually a variation of our two-step method, whereas the PNSR is a variation of our one-step method, but with different architectures than using a kernel method. So what Cindy does essentially is that for the first step, they usually either assume that U is known or they just use some classical techniques to recover the U, and then for the P function itself, what they do is that they use a library of these candidate functions, and they use in particular for burgers, it's a polynomial library, and then they try to recover the terms. And what PNSR people do is that they have again a big loss term, and they for the U, what they do is that they approximate it using a neural network. And then for the recovery of P, again, using some sparse regression techniques, they also have this library and they try to learn the terms. But that's done in one step as well. So they just have one loss term and they minimize that. And so here in the comparisons, so we're comparing our better method, which is the one-step method, against these two. And you can see that compared to the truth here, just our method seems to work better than both of these methods. And then we have the following error plots. So this is for the recovery of U, and this is for the recovery of P. And as you can see again, so the one-step method is actually performing better than the other two. So in everything that I presented, there's everything was essentially worked with low number of data points, and it was synthetic data. And now we're working on my group is working on some collaborations with a group at JPL that are focusing on a problem with real data. And also, so in this problem, for example, that they have, they essentially have a PDE of the following form, and then they have some data points, but they're not first of all, they're not sure if all of these terms appear actually in this differential equation. So one factor is that they have to account for model misspecification. So essentially, they have some unknown factors in the form of the equation, and they also have unknown coefficients. And so that all adds to this problem being a good problem to fit into the kind of method that we worked on. So significant differences is that they have real data and they have a lot more points compared to everything that we had on this work. And there's another project that's also, again, a collaboration between my group and another group at USC, and they're working on way more complex systems of equations with a significantly higher number of real data points to just essentially perform the same sort of tasks to solve their problems. And with that, I think that will be the end of my talk, and I'm happy to receive any questions. Thank you.
Yeah, thank you very much.